So in the first part of this lecture, we talked about some basic ideas behind structural materials selection, why we might pick, for instance, concrete over timber or steel over one of the other two. We talked a little bit about code requirements, flammability, fire resistance especially, and also a little bit about economics. And so what I want to do to sort of finish off this first lecture is to look at some case studies where we're thinking about both the material itself and also how it's fabricated, how it's turned into building components, how those components are assembled on the site. We'll look at a couple from history, and we'll also look at one contemporary example that focuses really on the methods of production and how those balance the overall budget along with the construction schedule to achieve efficiency in kind of one or the other. We talked at the end of the last lecture about kind of new modes of practice in the last 10 or 15 years, building information modeling especially, that helps us to get kind of ahead of the game in terms of thinking about how things are going to go together, that we're able to incorporate a lot of knowledge into our kind of early designs, and the curve of our efforts over the last 10 or 15 years has really shifted so that we do more thinking about construction and fabrication now in preliminary and detailed design than we used to. This helps us to make good decisions, but it also requires both a lot of knowledge about how these materials are made, where we get them from, how much they cost, what the labor is like to put them together, and how fabricators and contractors are going to actually do the work to put these designs together. This means of course, that a more integrated approach is always better. The more knowledge we can get from people who actually know how these things are going to go together in the factory and on the site, the smarter our designs can be, the more efficient they can be. We talked a little bit about the relationship, the contractual relationships that we have that sometimes kind of frustrate or stymie this, that we, of course, have a contract with the owner that involves subconsultants like structural engineers who are going to know about how the system has to perform overall. The owner is going to have a separate contract, of course, with a contractor who is going to have a contract with a subcontractor who will do the actual work. And so this sort of knowledge is contractually kind of difficult to assemble early in the project, unless we have a contract that allows for this kind of communication to happen more efficiently, right? So we can bring on expertise sooner in the design process rather than waiting until after a job gets bid to find out how a subcontractor is actually going to do it. It's a slightly different paradigm than we're used to. We still come out of a tradition of sort of master craftsmen or master builders, where the architect is kind of expected to know how certain materials, in this case a local stone, is going to get cut, is going to get crafted, where it's going to come from. Today, of course, we have a much more global supply chain for most of our building materials, something like steel especially, and so we may not have access to the kind of local craftsmen that, say, Peter Zumthor did when he did the baths at Vals, where he was talking one-on-one with the people who could actually put the stone together. We may still do that with some trades, carpentry, for example, but again, the contractual relationships we have usually mean that we have to kind of absorb this knowledge in general, or we have to have specific consultants that help us to understand these processes during the design phase. We have all kinds of new tools as well that help us go from design to fabrication, especially very quickly. And you all have seen these in studio, whether that's laser cutters or 3D printing. These can kind of scale up to help us create not only kind of model pieces or sort of product scale pieces, but actually large building components. And there are a few industries, steel especially, where this has been really dramatic. And we've seen a huge increase in the efficiency of fabrication plants and being able to turn out complex, often sort of mass customized pieces, or pieces with very complicated geometry that would have been very expensive back in the day, 10, 15 years ago, when all of this cutting and bolting and welding would have had to be done by hand. Now a lot of steel fabrication can be done using CNC machines, whether that's plasma cutters or robotic welders, to achieve much more complicated shapes than would have been easy to do a few years ago. We see too that things like building information modeling help us to streamline the fabrication process to make prefabricated parts, especially that are not only very specialized or very individualized geometries, but we can also keep track of these parts more easily. We can keep track of kind of multiple supply chains where different materials or components from different factories have to come together at various times. And so just as we use building information modeling to keep track of how the design is coming together, those same technologies, in some cases those same models, help fabricators and contractors to piece together to keep track of where all the various components are coming from. And in a lot of cases, those models will actually help them to make it. So they may be taking some of the same models that we're using to conceptualize the design. They can use that then to actually run CNC machines, to run robotic welders, to run the machines that are going to digitally craft a lot of the components to our buildings. This means a couple of things. One, it means that we can come up with forms that are much different, much more complicated than we could have just a few years ago. But it also means that we have different processes and different ways of making things that can really affect not just the building form, but also the kind of tectonics, right? The actual fabric of construction. It allows us to make much more efficient structures. It allows us to make structures that where we're no longer tied to kind of mass production. We don't have to make exactly the same thing hundreds and hundreds of times to get the efficiency out of prefabrication. We can use these processes of mass customization and let the machines, and especially the digital technologies, do a lot of the work of handling this complexity for us. You all have seen a lot of this in studio where you maybe are building much more complicated models because you can use things like laser cutters and 3D printing. And when we blow those things up and we're using actual CNC machines, whether that's routers or plasma jets or welders, we see, of course, that we can actually not just make little models, but we can make whole building components. And some of the areas where this is really interesting, here's a kind of plywood shell that is clearly used mass customization to turn out hundreds of very individualized parts. No one is the same as any of the others. But we can also use this for some of the traditional tasks that have taken a lot of skilled labor. Carpentry, for example, that goes into concrete formwork. For building a concrete structure and we're using timber formwork, we can use some of these same CNC processes to create more complicated timber formwork and therefore more complicated concrete forms in the finished product, finished building. We see this in other materials as well. So steel, we fabricate a lot of traditional looking steel shapes using robotic machinery, CNCs, but we're also seeing new ways of producing steel. So robots that weld individual, in this case, little form-active pieces together to create a very complex vector-active structure. This is a truss. All the elements of it are triangulated, but you can see that it gets away from our traditional sense of what a truss is, right? A truss we're used to thinking of as several standardized, similar shaped, similar size components. And here you can see that they are able to tune the elements of this truss, actually, an arch truss. They're able to tune not only the configuration of the truss, but if you look closely, you can see that they're also tuning the size of the elements. So they're using many, many different diameters to achieve a real structural efficiency, right? No piece is bigger than it needs to be. In a traditional truss, we have relied on the principles of mass production. So we would like to make the same piece again and again and again and again. We set up jigs, or we set up molds or standard dimensions, and we simply make the same piece hundreds and hundreds of times. And we're no longer really tied to that with these new digital technologies. We can again let the machines handle the complexity, handle the difficult geometries that would be harder for us to do if we were doing either of those things manually. We're seeing, too, that this allows us to use materials in new ways. So we see a lot of metals that maybe wouldn't be used typically in sort of older structural paradigms, but where robotic arms now are not only sort of welding things together, but they're actually producing things out of, for instance, molten solder, right, which you see on the left. On the upper right, plastics, of course, a very, very big material in 3D printing because it's easy to get plastic filament and to turn that into complex shapes. Plastics have usually been used in building in relatively small scale mechanical components, and today we're seeing much more use of them in broader situations. So cladding panels, larger interior panels, complex shapes that previously we would have had to design molds for, and that today we can often make with 3D printing. And a material that we'll talk about when we talk about cross-laminated timber. Timber is seeing a real comeback in part because it's so easy to fabricate complicated shapes out of two-dimensional sheets of plywood. Using things like laser cutters on a big scale, we can again handle much more complexity than we could have 15 or 20 years ago using digital technologies. We can use these in some cases to make much more efficient structural shapes, or as you see in the lower right, we can use these, of course, to create much more complicated, purely architectural shapes, right, that maybe don't have a structural logic. But again, because we can make these and we can also analyze these using digital tools, engineers can find ways of making these shapes work in ways that they wouldn't have been able to do a generation ago. And finally, we're also seeing some of these technologies applied to concrete. In addition to making formwork that's much more complicated for concrete, concrete, because it starts out in a liquid state, is very easily transferable to 3D printing technology. And we've seen some successful, albeit kind of preliminary experiments in this realm as well, where digitally controlled nozzles are sort of pumping out small layers of concrete over and over again, just like in a Potter bot or something that you would use in the digital lab today, but again on a bigger scale. You can see from these kind of early examples that the process is pretty imprecise, right? Not maybe as perfect or as beautiful as we would like. And you can see too that there are some limitations. Usually these days, 3D printing in concrete has been done kind of in the lab. So it's been used to make components. And transferring that sort of precise mechanical technology out into the real world, where again, just like in other concrete construction, we have constraints that have to do with temperature and humidity. We'd like to pour concrete in pretty good weather. And the material being kind of that finicky, that subject to changes in temperature or humidity, we're finding that digitally printing a concrete structure has difficulties in the real world, just like manually putting together a concrete structure. So these sort of processes all fit into the kind of paradigm for design that we've looked at all through the STP curriculum, the structures curriculum, where we have this iterative process where we are conceptualizing, thinking through a design. We're trying to put that design out into the real world, test it in ways that might be modeling first, but then also maybe full-scale prototyping, seeing how those work, and then very often sort of feeding that back into the thinking process. So rethinking, remaking, retesting, rebreaking, and using the models to kind of gain knowledge about how our ideas might or might not work out in the real world. This is really the point that a lot of these digital technologies are at right now, is we have some preliminary ideas about how they work, about scaling them up from the sort of desktop digital fabrication that we're used to in studio, seeing how they work when we apply those to something that's the size of a component, or in the case of 3D printed concrete, even a whole building. We're still designing for the physical world, so all of our kind of structural constraints still apply, right? Digital fabrication can't just get rid of gravity or lateral forces. What we have, though, is we have new ways to both test those, new ways to prototype them, and ways to fabricate more complicated geometries or more complicated networks than we would have had just a few years ago. So I want to look at now 3 case studies, 2 sort of historic ones and 1 more contemporary one that start to get to these ideas of looking at materials, looking at how they're fabricated, how we can take advantage of those fabricational methods and the properties of the materials themselves to gain efficiencies, not only in the way structures perform, but also in the way they're put together. And to me, one of the most interesting, one of the most sort of fascinating stories is of these kind of famous hangars that the Italian engineer and builder Pierluigi Nervi built in the late 1930s for the Italian Air Force. And these gained a lot of publicity at the time for being very advanced structures. They're sophisticated kind of in the physics and the way they work. You can see on the left, this is an interior shot where you can imagine that Nervi's kind of applying 2 or 3 structural ideas together. First, the idea of a surface active vaulted roof, and sort of melding that or hybridizing that with a principle called a lamella grid. So you can see these kind of intersecting diamonds that wrap underneath the vaulted concrete roof. And those interlocking diamonds, you can also see them as a network of ribs. You can see these in 2 ways. One is that those ribs are stiffening the curved vaulted roof, right, and making it keep its shape as a surface active structure. The other way you can look at it, though, is as a kind of coffering, right, like the Roman Pantheon, where the roof is sort of behaving as if it's 3 feet deep, but we've scooped out a lot of the dead weight of that roof and made it as light as possible. And you can see on the right, lightweight is important in this case because the roof has to be lifted up above the floor where the aircraft that it's going to shelter are going to be. And at the front of the hangar, of course, you need to be able to move these big airplanes in and out. So the roof not only has to carry the gravity loads, it also has to be lifted up above those doors, and it has to span over the hangar doors. And if you look closely, you can see that there's a long horizontal truss that over the openings that keeps the edge of the vault from kind of flaring out. And you can see, too, that there are a series of about 35, 36 buttresses around the outside that lift the concrete roof up and allow the hangar doors, but also some lighter weight enclosure walls to ring the hangar on the outside. So these were celebrated as kind of big advances in structural technology and in the use of reinforced concrete. Of course, it's a very complicated shape to build. And Nervi was sort of satisfied with the way they were built, but he also was a little bit concerned with a couple of aspects of their construction. One of the reasons that the Air Force, the Italian Air Force, commissioned a concrete engineer was that Italy has no native steel industry. There's no supply of iron ore in the country. And by the 1930s, the country had been embargoed by most of the world because Mussolini had taken over in 1922. He'd invaded Ethiopia, and the rest of the world sort of put Italy on a blacklist and wouldn't trade with them. So it was very difficult to get steel. And it was also very difficult to get timber. Italy is a peninsula that's been deforested since Roman times. And Nervi faced not only the problem of minimal steel, but also minimal timber for formwork. And reflecting on this first round of hangars, Nervi realized that as much attention as they'd gotten and as much sort of praise as they'd gotten, he had kind of fundamentally misunderstood the economic situation. And he wrote later that, you know, the problem with these was that you had to build them first out of timber and then build them a second time out of concrete. And all of the timber that went into that very complex formwork ended up being discarded. You can see, too, on the right that this is only a concrete structure in appearance. And because of the dead weight of all of that concrete in the vaulted roof, even with the lamella system, you can see what one of the connections looks like as all of these lamella ribs come down to those buttresses, right? That's essentially a steel structure with concrete kind of around the outside. All of that reinforcing is necessary to take the shear loads between the roof and those buttresses. So Nervi felt like, even though these hangars had come in for a great deal of praise, that they were too expensive, they had taken too much time, and they had taken too many resources, of which Italy didn't have very many. So a couple of years later, he's commissioned to do another set of hangars by the Air Force. The Air Force thinks that they came off just fine. It's just Nervi who sees these as a problem. And what Nervi does is he starts to experiment with precasting concrete. And this lets him do a couple of things. One, he realizes that he doesn't need to build the hangar out of timber first, right? If he breaks the problem down into hundreds of little precast units, he can build these with just scaffolding, right? With no formwork that he has to get rid of. You can see, though, that he's also experimenting with the section of those precast units. And instead of making the arches, the lamella arches, out of solid concrete, he realizes that with precasting, if you're doing that in a separate casting yard, you can get much more precise shapes than you could if you were trying to build the formwork in situ. So he starts to look at taking material out from what we know would be the neutral axis of that arch, right? So that it's you have basically two concrete flanges that are taking local bending, and you have just enough cross section to take the compressive loads that the lamella arch needs to take. This saves a lot of weight. It potentially saves a lot of time, since you can cast all of these pieces while you're digging the foundations for the main hangars. And it takes advantage of the one thing that Italy does have in abundance in the late 1930s, which is unskilled labor. Lots of people to put to work, and Nervi realizes that if you just mass produce these arch elements, you're not using very much timber, right? You're just making one mold, and you're telling a large crew of laborers to just do the same task over and over and over and over again. And so here is that second round of hangars. In the picture on the left, you can see a bunch of these precast truss elements in the foreground. You can see in the background there is a scaffolding, no longer a formwork. And on top of that scaffolding, crews of workmen would simply winch these elements up into place. They kind of glue them together with a little bit of reinforced concrete and a little bit of rebar that you can maybe see sticking out of the ends of the trusses. And then once a section of that had cured, they could move the scaffolding down, scoot it along the axis of the hangar, raise it into place, and start to work on the next kind of bit of the roof shell. On the right, you can see before they put a lightweight asbestos shingle roof over it, this is what the shell looks like, as opposed to that very heavy, solid, poured-in-place concrete roof in the earlier version. Same shape, right? Roughly the same dimensions. If you look closely, you can see that now, instead of 34 concrete buttresses holding the weight of that heavy roof up, Nervi has reduced that to 6. 2 at each end and 2 right in the middle. So now the hangar doors can go on either side. He's reduced the amount of concrete, eliminated the timber formwork, and because the roof is so lightweight, he's also reduced the amount of steel. So lots of economic pressures. I think you could even argue that there are political pressures coming to bear on these projects, and someone who understands what a material can do in 2 very different ways. One in which it's poured in place on site, resource intensive. Another in which it's actually fabricated in a casting yard, brought to the site and winched into place. So resource economical and very, very labor intensive. And labor, again, is something that there's plenty of in wartime Italy. A very different kind of setup, but also looking at the way that prefabricated elements can work, comes with this project. This is an experimental housing block in Montreal, Canada, done for Expo 67 by Moshe Safdie, who was, when he designed it, just a graduate student in architecture, and August Commandant, who was an engineer who specialized in pre- and post-tensioned concrete. And what Safdie's idea was that you could prefabricate all of these apartment units in a factory offsite. You could drive them to the location, and you could use cranes to winch them together. So again, like in the second round of Nervi hangars, using prefabrication to exploit the ability to precast concrete. So all of those units can be made in a factory while the foundations are being poured. They can be brought to the site in kind of a just-in-time method. It's a crowded urban site, as you can see on the left. So they don't have a lot of space to store things. You drive each unit to the site when you need it. You winch it into place onto a concrete frame. And because all of these units are built in a factory, they can be made to very, very precise tolerances that you couldn't ordinarily get with site cast concrete. There is a sort of poured-in-place scaffold onto which all of these are applied that has circulation that carried all the mechanical systems and things. But you can see also that there is a way to do kind of an early version of mass customization. There are about 8 or 9 different apartment units that the factory was set up to make, and those were put together, as you see in the upper right, in the studio in a way that made this incredible kind of variety, both in the sort of texture of the building, but also in the spaces that it created. And even though it looks like this is a collection of hundreds of different units, right? It almost looks like a kind of Italian hill town. It's really made from a kit of parts in which there is a great deal of standardization involved. And among other things, one of the kind of standardized elements, of course, is that these could only be a certain size. They had to actually get brought to the site either by ship or by truck. And so there's a limitation on how big the prefabricated units could be. Safdie worked to find ways to combine these so that you could create apartments of different sizes. But there is a kind of standard dimension that's given to all of us really by the fact that whatever we make in the factory has to actually get put on a truck or put on a train, or in this case, in some cases, put on a barge and brought to the site. There's also obviously a limitation in what we can lift. All of these are getting picked up by cranes. They're relatively heavy prefabricated elements, so they're big cranes, but you can't get a crane that's infinite in capacity. So there are limitations both in the dimensions, so that the unit can fit on a truck or a barge. There are also limitations in what each element of a building can weigh. Concrete, even when it's prefabricated, is still a fairly heavy material. Here you see some of the design drawings. You see on the left, those are kind of some of the sort of construction details. Commandant used post-tensioning. You can see in drawing C there a drawing of the detail at the end. So these sort of supercharged stainless steel tendons that press the building together and that allow each unit to work not only as an enclosure, but the real kind of genius of Commandant's work is that each one of these works as a section-active hollow beam. So the concrete walls that are on either side of the unit, they're keeping out the rain, they're insulated, but they are also reinforced so that they can take a great deal of structural loading. And one unit can serve as the kind of a cantilever bracket for a unit that goes on top of it. You get some idea for how that works in the drawing on the right, a section drawing that shows how these units are both tied together, and they're tied together again using post-tensioning, but also how they continually sort of cantilever out so that you get these very, very big, very, very dramatic kind of public spaces that the units kind of loom over. And also the ability to have one unit serve as the kind of terrace for the unit above it so that everyone gets a little balcony, a little garden space. This is what a precast factory looks like. This is a particularly large precast unit, but you can see that there are things that are analogous to what you would see on a concrete job site. There is formwork that, of course, is molding the concrete. There are inserts that go in to block the concrete flow and to create openings for doors and windows. There are embeds that are going to connect with steel in other units so that they can tie these together. And you can't see it here, but there are also channels that are cast for all of the post-tensioning cables that the Commandant specified. Even though this is a concrete job site, because it's in factory conditions, they can control the temperature, they can control the humidity, they never have snow days, they never have rain days. So you're able to keep to a schedule, and you're also able to ensure a much higher level of quality and a much higher level of precision than if you were casting all of this concrete on site. Here you see a construction shot. You get some sense both of how these units fit together, and also some of the potential for the cantilevering that the post-tensioning allows, right? Really dramatic spaces underneath. And here a more contemporary image looking up. The bridges are actually poured in place. Those are the circulation, but also the kind of main structural frame. And then you can see, using post-tensioning, how these kind of elements can cantilever out and create some of those overhangs in spaces. The weathering you see is 40, 45 years of rain and snow and ice. The quality of the concrete, the coloring of the concrete, the consistency, as you can see, is much better than you would normally expect in an in situ project, right? This is all because of the quality control that you get in precasting. This is all knowledge that Commandant brought to the project, right? He was able to coach Safdie, who had never really built anything before. He was able to coach him through how to get all of this quality into the concrete. And maybe a more contemporary example of this is the Atlantic Yards high-rise by Shop Architects, that again relied on modularity, prefabrication, but using a very, very different set of vocabulary. Shop and Arups not only designed the buildings, but they also designed a lot of the process. And some of that even involved developing apps where they could keep track of individual prefabricated units. So on a very, very tight urban site, right in the middle of Brooklyn, right next to the arena, Barclays Center Arena, they, of course, have to keep track of where all the modules are. They can only put a few of them on site at any given time. And they want, of course, to be able to use the crane constantly. Right? The cranes are expensive to have on site, and so you want to make the most use of them in the shortest amount of time possible. So they developed these apps to keep track of where the modules were in the factory, to keep the kind of supply chain of material running to the site, but also to keep it efficient. So there was never more than one or two modules sitting on the site waiting to get craned into place. Here, a diagram sort of showing how the process worked. You can see here the modules are actually out of steel, and they all have internal steel frames that are connected together. And as you can see, what they're doing is they're creating really a giant three-dimensional truss. And all of those triangles will both take and distribute the gravity loads from each module. They'll also, you can imagine, give it a good bit of lateral stability, something that we'll talk about later in the class. The modules not only came with the structure, but also with a lot of the interior fittings, especially bathrooms and kitchens, already installed, right? Put together in the factory, both to save time on site, but also to take advantage of the really controlled conditions in a factory to get a lot of the really sort of fussy, precise work of plumbing and electricity or electrical systems done, both offline in terms of the construction process, but also in a place where they could be carefully controlled and where they could have the kind of ideal environment for doing that sort of work. So here you see a sequence drawing. They, of course, had to coordinate various trades in the factory in which they were putting these together. But you can imagine setting up an assembly line so that you have a steel crew that's putting the structural frame together, maybe a carpentry crew that's putting together the bathroom module in this case, finish crews that are coming in and installing all of the drywall, flooring, ceilings, electricians and plumbers coming in and then fitting all of the toilets and the lights and things together in a way that could be controlled, in a way that could be predictable, and in a way, again, that was separated from the schedule on site. So all you're really worried about is the pace that these can be assembled in the factory, how often they come off the assembly line, how long it takes to get from the factory to the job site, and what the crane is going to need in terms of time to get one of these into place. And with the software they developed, they were able to sort of create this very, very efficient assembly line process, right? Similar to ways that we've traditionally built cars. Structurally, these modules take advantage of steel. They are, of course, assembled out of pieces of normal W shapes, but you can see that they're welded. They're welded again in the factory so that you get these very, very rigid boxes that make up the modules. You can see the kind of bracing. If you squint at it again, it makes this look like a truss. And when you stack a bunch of these modules together and tightly connect them, you will get trusses that distribute both the gravity load and the wind load throughout the structural frame. Here you see kind of overall. We'll talk a lot about kind of vertical wind trusses. The important thing for our point now, for the point we're trying to make now, is that this takes advantage of steel fabrication, takes advantage of the fact that you can put that steel together using, in some cases, robotic technology, in some cases, manual welding, and that you can create out of lots and lots of little pieces a very, very rigid structure that in this case can support a 35, 40-story building. And here you see the advantage. The modular schedule allowed them, they thought, to cut about 10 months out of a typical 30-month schedule. And that 10 months, of course, is 10 months that you're not paying a construction crew. It's 10 months that you're not paying for all the equipment to be on site. It's 10 months of rent that the owner is making instead of 10 months of rent that the owner is essentially paying for all that equipment. So treating the construction process more as an assembly line than a craft led to this savings of about 33% in the schedule and a roughly proportional savings in the construction budget. Project is finished now. These are renderings done at the time, and you can see that part of the designer's remit here is to take standardized units, or in some cases mass customized units, and to find ways to create an architectural language out of them. Shop in this case chose not to show off any of the trusses or any of the kind of steel work that holds the thing up, or that really sort of makes each module, very much like a car, right, with the chassis and all of the finishes and exterior things sort of put onto it afterwards. Nevertheless, it's kind of a reasonable piece of architecture made out of this very, very efficient process. So these are things that we'll look at for the rest of the module, both what the materials can do in terms of structural performance and how they're actually made, and how we can take advantage of what we know about both fabrication and assembly on site to balance what may be very, very thorny problems about both material costs, schedule, but also things like labor costs, right? Balancing performance with the way that we actually assemble these on site.